Hello everyone, welcome back to video lecture series on VLSI design. My name is Dr. Prashant Bachanna, working as Assistant Professor in the Department of Electronics and Communication at Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this video, I'll be talking about IDS versus VDS characteristics relationship of the MOSFET. So as all of us know, in the previous section, we have seen the working of the MOSFET. So now I'll see what is the relationship between the drain to the current from drain to source and the voltage. So let us say we'll take the structure of the MOSFET. Okay. So here let us say it's a N-type transistor. Okay, this is the source. This is the gate, and this is the drain. Okay. And it is lightly doped with the P-type substrate. So now this is the symbol of the transistor, that is N-type transistor. Okay, this is gate, let us say, and this is source and the drain. Okay, so now we have seen the working of the MOSFET. That is the gate voltage. The gate voltage is used to control the flow of voltage from source to the drain. So that is our concept. Okay, so the flow of current is controlled by the voltage applied. So the whole concept lies on the control of the gate voltage. So which will control the flow of voltage from source to the drain here. So by varying the gate voltage, we can control the flow of current from source to the drain. So under the condition that if you want to control this the flow of electric field, okay, so the flow of electric field generated by this current under the control of, so there is one condition, under the control of the VDS, that is the voltage applied between the drain to the source, that is VDS. Okay, so the gate voltage is used for the flow of electrons, and we can control the electric field by varying the VDS. So now we'll see the relationship. What is the relationship between the VDS and the IDS? That is the current flowing from, if you increase the voltage, the drain to source current will also increase. So that is the concept. So we'll see what is the relationship between the IDS and the VDS of the MOSFET, that is IDS versus VDS relationship of the MOSFET. Okay, so this is the structure as we have already seen. It has the terminal, source, gate, and the drain. Okay, so it is having of the length L, we'll imagine, and the width W. So let us say for this relationship, we'll see as already we have seen, the flow of current is directly depends on the VDS applied. So we can write IDS is equals to minus I of SD, that is conduction charge induced in the channel divided by electron transit time. So the current flowing in the transistor depends on depend on the ratio of whatever the charge induced in the channel divided by electronic transit time, and the electronic transit time is given by the length of the channel divided by velocity. That is why the length of the channel plays a very important role here. So the length of the channel is less, the electron density will be more, and the flow of current will be more. So with this we can write the velocity as V is equals to mu into EDS, where mu is the electron or the hole mobility. So if it is an N-type, based on whether the transistor is of N-type and P-type, so the mu is the electron mobility, and EDS is the electric field from the drain to the source. So as we are already seeing here, okay, drain to the source. Also, since source and drain terminals are integers, we can write VDS. So we can write EDS is equals to, from this equation we can write EDS is equals to VDS by L. Then what we can write, now we'll see then again we can write the V is equals to, that is mu into VDS by L. So thus we can transit time, the electron transit time from electron or the whole transit time from source to the drain is given by L square divided by mu into VDS here. So here mu n and mu p are the electronic mobility of electron, that is the constant here, that is 650 square centimeter per volts, and this is mu p 240 centimeter square per volts. This is on the surface of the surface. So these are the two constants, that is mu n and mu p. So as we have seen in the previous class, that there are three regions of operation, that is saturation region, non-saturation region, and active region. So in the non-saturation region, as shown in the figure, we can write the equation, that is the total voltage Vg can be written as Vgs minus Vt. Okay, so this is the condition for the non-saturation region. So Vgs is equal to, Vgs is the gate to source voltage and Vt is the threshold voltage. So, threshold voltage is the voltage at which the transistor is turned on. And from this, what we can write in the non-saturation region, in the non-saturation region, there will be a little bit flow of current, but the transistor will not be on. So we can write QC is equals to here Eg, that is relative permittivity INS, and mu naught W into L. So where Eg is the average electric field from gate to the channel. Okay, so then epsilon NS is the relative permittivity of insulation between the gate and the channel. Then epsilon naught is called as the permittivity of the free space, and these are the constant here. Epsilon naught, that is 8.85 into 10 to power minus 14 centimeter. So, and these are the constants. Then from this equation we can write easily the EZ, that is what is the electric field generated in the non-saturation region. From this equation we can directly write it. So if we substitute the value of Vg is equal to Vgs minus Vt, then we'll get this equation. Okay, so then if D is the oxide thickness, then we can solve this equation. So then we'll get, so at the end what we can write, so now combining above three equations, we'll get finally equation for this IDS, that is IDS equal to K into omega by L, Vgs minus Vds, Vds minus Vgs minus Vt into Vds minus V square by 2. Okay, so where K is the constant. Okay, so this is the equation for equation in the non-saturation. So as we can directly see that the current is directly depending on the voltage as well as the voltage that is Vgs minus Vt into Vds. Okay, so the factor W by L. So if to calculate the beta K into omega by L, so we can write, so where beta is equals to K into omega by L. So we can easily write the above equation as IDS is equals to beta into Vgs minus Vds minus V square by 2. Vds square by 2. So this is the equation for this is the relationship between the current flowing from drain to the source to the VDS. So here VDS we have, so we can directly say that there is a relationship. As we increase the VDS, there will be a change in the current. Then we can use these channel capacitance also. The formula for the channel capacitance is Cg is equals to permittivity of I n epsilon naught WL divided by T D, and here is again the constant. Okay, so again we can write this equation. If you substitute the value of the gate capacitance here, so we'll get this equation, and again substituting the value of C naught and C naught, that is C naught is the capacitance per unit area, okay, which is often called as the Cox. Okay, so we can easily write Cg is equals to C naught WL. So also we can write this equation as IDS is equal to C naught mu into W by L, Vgs minus Vt into Vds minus Vg square by 2. Okay, that is about the non-saturation region. Now we'll see the difference between the saturation region and the non-saturation region. So in the saturation region, what is happening? The Vds is equals to Vgs minus Vt. This equation will be there. Okay. So here we assume that the current remains fairly constant as Vd increases. So as all of you know, in the saturation region, we'll see that the current flowing from IDS, that is whatever the current flowing from the drain to the source, will be constant, because in the saturation region the transistor will be on here. So here we can write this equation as IDS is equals to K into omega by L, VGS minus VT squared by 2. So here you can write simply this, or we can also write it as, instead of, we can substitute the value this as beta. So beta by 2 VGS minus VT whole square. So this is the equation between the this is the equation of the relationship between the IDS and VDS in the saturation region. So in the saturation region, the transistor will be on, and the drain to source voltage will be equal to VGS. The VGS is greater than VGS minus VT, or greater than the threshold voltage. Okay, so again we can substitute the value of the capacitance and this thing. So finally we can write it as IDS is equals to C naught mu W by 2L VGS minus VT whole square. This is the final equation for this this one. So as the expression is written as the IDS holds for both the enhancement and depletion type transistor. So for both the transistor is same. Okay, so as you can see, the depletion region also, as you can see, there is the graph on VDS versus IDS here. So as we are increasing the gate to source voltage, the current is also increasing, as you can see in the graph easily. So this is called as the saturation region. See, in the saturation region, the condition is VDS is greater than VGS minus VT. That is in the in the saturation region. Whereas in the saturation region, in the non-saturation region, VDS is less than VGS minus VT. Okay, so that is the condition, as you can see in this graph. So for the enhancement type is also almost same. As you can see, in the saturation region, the drain to source voltage, that is like we are discussing IDS versus VDS characteristics. So if the VDS is greater than VGS minus VT, at this point the transistor is in the saturation region. So as you can see, there is an increase in the if you increase VDS up to a point wherein the transistor will be on, that is VGS minus VT. So at that time the flow of current will be constant. There will be a constant flow of current will be there. Okay, constant flow of current from source to the drain terminal. So this is the relationship between the IDS and the VDS characteristics. In the non-saturation region, this in the beginning, as you can see here, VGS equal to 0.2, 0.4, all these values, the transistor will be in the non-saturation region. There will be a small amount of current which is flowing, but the flow of current will not be sufficient to run the transistor. So at this point, that is in the saturation region only, we can say that the transistor, the flow of current is constant and the transistor is on. So the aspects of the MOS transistor threshold voltage. So now we'll see the importance of the threshold voltage. So the gate structure of a MOS transistor consists of electrically charges stored in the dielectric layers and the surface to surface interfaces, as well as in the substrate itself. So the threshold voltage is the voltage at which the transistor will be on. Yeah, this is the equation for the threshold voltage. That is, threshold voltage is equals to psi into Ms QB minus QSS divided by C naught plus 2 into psi of Fn. So where C naught is the capacitance per unit gate area, psi Ms is the work function difference between the gate and the silicon, and psi Fn is the Fermi level potential between the inverted surface and the bulk silicon. So as you can, again, we will see this the derivation in the coming class. So this is the summary of the IDS versus VDS characteristics. Okay, so in the non-saturation region, as you can see, as I have already mentioned, the VDS is less than VGS minus VT. Okay. So the equation, we have to remember this equation, that is IDS equals to K dash N omega by L VGS minus VT into VDS minus 1 by 2, this one. So the saturation region and in the pinch off region, there will be 3 regions of operation, right? The first one is called as the pinch off region, wherein which is if VDS is equal to 0, there will not be any flow of current, that is pinch off region. Then non-saturation and the saturation. The non-saturation region, VDS will be less than equal to small amount of current flows in the non-saturation region. So you have to remember this equation, and the most important equation is the saturation region, wherein the VDS is equal to is greater than VGS minus VT. That is the condition. Okay, so this is the equation, that is K by 2 omega by L VGS minus. As you can see directly, that the flow of current is directly dependent on the VDS here. It is So these are the references we have referred. That is Bucknell Bucknell, then the Jacob Baker. So these are the references which I have used for preparation of this slide. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.